Okay, so I think we'll make a start. So welcome to the 12th session in our Society of Chemical Industry webinar lectures. Today we're going to be showcasing the winners of the National Retrosynthesis Competition 2020. Those of you who don't know me, my name is Oliver Ring. I'm a process chemist at AstraZeneca, and I'm also joined by Jason Camp from the Fine Chemicals Group and Nessa Carson. I'm going to be your host for today. So those of you who aren't aware, the SCI aims to break down the barriers between industry and academia, and we do this by organising various events, conferences, including today's webinar session. So for those of you who are new to the series, all delegates are automatically put into mute mode. We're going to have 3 teams talking today and 5-minute Q&A sessions after each talk. So if you have a question, type your question into the questions tab and we'll aim to prioritise as many of those as possible. At the end of the session, we'll also have an open panel discussion where if you have questions which you want to ask using the audio, then please raise your hand and we'll aim to prioritise those and get that sorted out. If you want to ask a question using the audio, please get a headset set up in advance. It's worth noting next week we've got a talk from Neil and Anya from Merck on electrochemistry and biocatalysis. This is going to be our last talk of the series, so definitely worth not missing that. It's going to be really good fun. So we hope to see you all next week as well. And I'd like to thank all of our corporate partners and sponsors. So we've got AstraZeneca, GSK, UCB, who are our corporate partners for the whole webinar series. And then today we've also got Liverpool Chirochem sponsoring this particular webinar session. I'd also like to thank the original sponsors of the National Retrosynthesis Competition as well. So we've got Pfizer, Syngenta, Signature Discovery, Thermo Fisher, Vertex, Concept Life Sciences, and Charles River. So thanks to all of those companies for supporting us and making this possible today. And then also I'd like to thank the original organising committee who did a great job at organising all of this. Yep, so this was a sort of cross society event that was organised by different organising committees. So we've got Jason Camp from the original from the Fine Chemicals Group. We've got Kiri North from the Young Chemists panel, and then Susanna, Mark, Rob, and Dave from the Royal Society. So thanks for all of you guys for doing a really good job at organising the original event, and hopefully we can showcase some really cool chemistry today from the winners. Okay, so just introducing the molecule. So the retrosynthesis molecule nidoterpenoid A, it's a sesquiterpenoid, which is a particular class of terpenoids, which is synthesized biochemically as a secondary metabolite of Aspergillus nidulanus, which is a fungus, as shown in the image just here. And also we've got the image on the side here of the cardinal heads from the individual fungus spores. So this is the first example of a highly congested hexacyclic carbon ring system with this sort of 5-5-5-5-3-5 ring system. It's incredibly complex. It's got 13 chiral centers, and it has potential applications as a tumor cell proliferation inhibitor, notably for breast cancer. In terms of where this is from, we've got this map here. So this is the fungus originates from the Hubei province of China. Hopefully I'll pronounce that correctly. So if we zoom in here, which some of you may have seen in the news recently, as this is, or the capital of this province is Wuhan, which of course is where COVID originally started. In terms of how this is isolated, originally this was fermented on a solid substrate medium of 30 kilos of rice. Is then extracted using ethyl acetate and then purified using various rounds or a number of rounds of flash chromatography and PrEP HPLC to give you crystalline solids. Okay, so our first team we've got from Evotec. This is made up of Inoa, Angelo, and Tim, who are senior scientists at Evotec, and then also James, who is an industrial placement student. And their fun quote is, or fun quote for the session is, we like our molecules to be more basic, which I'm sure will become obvious as they present their retrosynthesis. Okay, so I think without further ado, I'm absolutely delighted to hand over to you guys. I think we had some minor issues in terms of audio and visuals, so there might be a bit of switching between laptops, but hopefully it works okay. So I think if we pass over to Angelo.
Hi guys, so thank you very much for the introduction, Oliver. So I'm Tim, and I'm going to be starting our route. We begin our retrosynthesis with carbon-carbon disconnections to the main hexacyclic core. So after a second disconnection, a key disconnection, we can break apart our western and eastern fragments. And then our third key disconnection is to simplify this 5-3-5 core. And so in our forward sense, we can introduce this at a later stage. And then finally, we recognized similarities in our western and eastern fragments in terms of these cyclopentanone retrons. So we begin our western fragment synthesis with this commercial alcohol. We can brominate it, magnesiate, and then the Grignard will add into a propanol in a 1,2 selective manner in good yield. We can then protect the resultant alcohol and oxidize to provide the substrate for our first Powelson-Cahn reaction. And using this titanium catalyst on the right-hand side, this is well precedent to go in excellent yield and good EE. So with our fused ring system in place, we can treat with cerium trichloride and methyl lithium, conditions which favor attack at carbon 26 over carbon 23 of the enone. And then we can protect, and then because of the exocyclic face of the molecule, we'll attack from the bottom to provide this desired stereochemistry. So we can protect the resultant alcohol with TBS chloride, and then treat with Lucha conditions, which favor attack now at carbon 23, the enone in a 1,2 selective manner. And again, the bulk on the top face and the exocyclic selectivity of the molecule allow for the desired stereochemical outcome from attack at the bottom face. So that completes the western fragment. The eastern fragment, and this is part of the elegance of our approach, we hope to convince you, we begin with the same commercial alcohol and oxidation of 1 to acid 7 and double addition to ester 8 to provide the divinyl tertiary alcohol 9 allows a simple esterification and a substrate for my favorite reaction on synthesis, this diastereoselective desymmetrizing Powelson-Cahn through this prochiral divinyl ester species with this binap-derived iridium catalyst. And we're setting the stereochemistry at carbon 6 and 4 in a step. So to go through this in a bit more detail, we think of this Powelson-Cahn through our reading of the literature as going through a chair-like system where the large group will of course prefer to go equatorial, and the methyl and vinyl A values describe this. So we want the large group to go equatorial, and this will give the desired defined outcome in 11C in the general case. But with our methyl and vinyl groups having poor differentiation, we think there should be a poor DR for the methyl at carbon 6. So instead, we've bulked out with a TMS group to enhance the substrate bias, and this gives us the bulky TMS methyl group at in 10F equatorial, and this should give the desired stereochemical outcome in species 11. So I'll pass over now to our next presenter.
So we move now towards the completion of the eastern fragment. A chemotherapy considered the privilege of interesting design group, which is controlled by that we do simultaneously the aldehyde, the lactone to the lactone, and reach selectively the enone. Because of the approach of the aldehyde from the top phase, this reduction would also be stereo controlled, as you can see. Finally, we exploit our universal sealing protection strategy by efficiently protecting all the alcohols under the same reaction conditions. An enantioselective addition of alkyne to aldehyde 14, trapping the resulting alkoxide with the acetyl chloride, will prepare the eastern fragment for our next key step, the Rutherstrauch cycloisomerization. This newly generated stereocenter is crucial in order to achieve the desired stereochemical outcome later on. Here we show on the bottom left the proposed transition state of the alkyne addition to explain the rationale for the stereoselectivity. As you can see here, there is a steric clash between the alkyl group of the aldehyde and one of the ligands of the zinc, determining the facial selective attack. At this stage, we also consider a more elegant approach to install the chirality as C12. From a closed intermediate, we could implement an alkyne addition under substrate control via the magnesium 1,5 chelation control, via the formation of an 8-member ring. Overall, this approach, however, will be one step longer. Our preferred route is more direct, provides more robust stereo control, and maintains our universal protection, sealing protection strategy. Lastly, a chemoselective DTMS in the presence of an acetyl and 3 sealing protected alcohol will finally deliver intermediate 16. So we now get to our second key step, the Rabenstrauch cycloisomerization. Using a proper Gillick ester in this case as a simple and severe alternative to alpha-diazokitone. Here we have a small scheme with the mechanism. An initial activation of the terminal alkyne by complexation of the platinum catalyst is followed by cyclization with a rapid formation of the 5-3-5 system, as well as 3 new stereocenters. This will be followed by the migration of the acyl group from the carbon 12 to carbon 13. The stereochemical outcome of this reaction is strongly influenced by the stereochemistry previously installed at C4 and C2, who substitute and shield the bottom phase of the alkene, and also by the relative stereochemistry between these two carbons and that at C12, which make this step highly stereoselective. Lastly, a mild acetal hydrolysis would deliver our complete Eastern fragment 18.
Okay, so after Tim and Angelo has shown the synthesis of the Western and Eastern fragments, it's time to link them together to form 22. And for that, we consider 2 main options. A Sujitrow's reaction, which will be one step shorter and will imply the transformation of alcohol 6 into phosphate 19, and a Claisen rearrangement of the corresponding O-alkylated enolate, which will require first the preparation of sulfate 21. Starting with the first option, so after the formation of the copper enolate, represented here as this R group, the coordination to the alkene from the opposite face of the phosphate group results in an equilibrium between these two species, in which the enolate of 18 is placed either far away or closer to the phosphate leaving group. Now, while the latter will give rise to the undesired but more common linear isomer as a result of a formal SN2 reaction at carbon 23, our catalyst system prevents this path in favor of the branched SN2 prime outcome instead, providing compound 22 in an overall inversion of configuration. But not only is this reaction stereospecific,
stereoselectivity plays in our favors the formation of a syn 5-5 ring junction at, in the product, together with the steric hindrance in the top face of the Western fragment, will direct the approach of the enolate to the exophase of the bicycle. Now, with regard to the Eastern fragment, you can see how methyl 15 on the cyclopropane ring shields the bottom face of the enolate, forcing the approach to the Western fragment from the top face instead. As a result of all these factors, the Sujitrow's proceeds with excellent regio and stereo control. Focusing now on our alternative Claisen rearrangement strategy for the convergent step, the key here is achieving the regioselective O-alkylation of the enolate of 18. In this regard, the use of neopentyl sulfate 21 favors the formation of vinyl ether 23. Here, the inversion of configuration at carbon 23 sets the ground for the facial selectivity of the Western fragment in the subsequent Claisen rearrangement, which in this case is promoted by Lewis acid. The facial selectivity of the Eastern fragment is determined by the rigidity of intermediate 23, which can only offer a good orbital overlap when the Western fragment is situated on the top face of the vinyl ether, as shown in this 3D model. And indeed, you can see here our proposed transition state in gold, which adopts a bot conformation, showing clearly the dual facial selectivity of this rearrangement.
After merging both fragments, an interrupted Corey-Fuchs reaction generates the geminal dibromoalkene 24 that undergoes a highly regioselective intramolecular Heck reaction. Initial chemoselective palladium complexation to the more electron-rich alkene guides insertion into the proximal CBr bond, and 5-exotrig cyclization and beta hydride elimination follow to produce vinyl bromide 25, which is less reactive than 24, allowing for a selective monocoupling. The facial selectivity would be determined by the stereochemistry previously set C12 and C18, and by the formation of a SYN55 junction between C18 and C19 in the product. Hydrogenation of diene 25 using a heterogeneous rhodium catalyst delivers the fully saturated carbon skeleton of 26. Again, the facial selectivity is driven by the formation of a SYN55 ring junction between C12 and C13, and this sets the desired stereochemistry of the secondary bromide for subsequent SN2 reaction. The dimethyl Gilman reagent now displaces the bromide of 26 with inversion, and here we would want to highlight the accessibility of the LUMO towards nucleophilic attack, as shown by the red lobe here. Lastly, a simultaneous global deprotection of not only all the alcohols but also the CTMS group affords neoterpenoid A. In summary, we exploited elements of similarity hidden in the molecule and rapidly generated complexity during the installation of the key cyclopropane ring. Our convergence step can be achieved using 2 highly stereo-controlled routes, and a final HEC reaction completes the hexacyclic core. The highly convergent synthesis has a small step count and a 21% overall yield, and after early introduction of chirality, all subsequent steps are under substrate control. Thank you for listening, and we hope we showed that with Pawson we can.
Hi guys, that was really nice. Sorry about the audio. I hope that was clear enough. I think we were having some problems before, but hopefully we're okay with sharing laptop screens. Just got a quick question before I hand over to Jason and Nessa. For the Claisen rearrangement, do you mind just going to that slide? Yeah, I mean, I just wondered how likely that reaction would actually take place. You've just got a really congested electrophile, which is sort of at the bridgehead, and you've got a methyl group there as well. So how likely is that going to actually, or how much precedent is there for that kind of chemistry in that position?
There is precedence. We believe that in this case, the orbital overlap could be good enough looking at this model. And we have some examples in the, we found examples in the literature where a congested systems have been used. So I can show.
Okay, yeah, so it is possible basically.
And the Claisen rearrangement has been widely used for the formation of very congested systems. The steric hindrance surely plays some kind of role, but quaternary stereocenters also as well as vicinal quaternary stereocenters have been widely synthesized using this methodology. Yep. So as long as the transition state is allowed, whichever is like as a chair or a both transition state, as it looks like in our case,
yeah,
there shouldn't be any problem in the reaction occurring.
Cool. Thanks. So I'll just pass over to Nessa and Jason for the Q&A. I think we've got a couple of questions coming in.
Excellent. Thanks for that, guys. Great talk, and thanks for overcoming the audio issues. Just a quick reminder, if you do have questions, please just type them into the chat as best you can, and Nessa and I will run through those. We're going to try to keep this to a total of 5 minutes of questioning, just to keep everything fair for all of the teams, and that way everything sort of balances out on balance. If I may, just before we jump into the questions from the audience here, just a quick question on slide 7, fairly simple, but I thought you might be able to address this very quickly for me. Perfect. It's just about the formation of that compound 9 there. I wasn't sure if that was a literature protocol, and if it wasn't, if you were worried about a Brook type rearrangement where the TMS group's going to migrate onto your alkoxide.
Yeah, fair cop. So I forgot to mention in the actual presentation itself, in March, I was better at this bit of the speech. So the formation of the tertiary divinyl alcohol is precedented to occur without Brook rearrangement or Peterson elimination. I think the stability of 10, for example, might be problematic under acidic conditions, but as it is, we found good literature evidence for the stability of these things. The carbon TMS itself appears to be stable through all the sets and conditions subsequently after the formation of that carbon TMS bond, or incorporation in this step.
That's great. And my apologies if I asked that at the competition. I've probably forgotten by now.
No, I remembered to say it in the competition. It's just
Nessa, it looks like we've got one there. Do you want to try to read the one out for us?
Yeah, thanks very much for that talk. That was really cool synthesis, really interesting work. So we've got a question here from Matt Fuchs, who he's asking, how confident are you that the 5-3-5 ring system is going to survive right the way through the synthesis without ring opening? Because I guess you have quite a few steps with that 5-3-5 there.
Yeah, I'll carry on and answer this if I may. So the 5-3-5 system is stable to some things and not everything. What we found was that if you have the enolate formed, or you have the chance for a radical style like a clock type decomposition, if you have adjacent radicals forming, then you can collapse the system in that kind of way. In some palladium enolate type conditions, you could lose that kind of 5-3-5 system. But under the conditions that we had, we felt it should be stable. There's a certain amount of congestion as well around preventing some kind of type decompositions. That kind of goes some way to answering.
No, that's great. Thanks everybody. And that's your 5 minutes done there. So I'd like to thank everybody again. I'm sorry we can't all clap. It would have been 136 people clapping, which would have been quite nice. But thanks again for presenting today. And if I can add back Oliver, and he'll pick that up.
Yeah, thank you very much, everyone.
Okay, so our second team, who unfortunately aren't available to present today, but we thought we'd share some of their chemistry anyway, just as sort of well done for coming third place. So we've got Tim and James from University of Oxford and UCB, and their team is the Frustrated Lewis pair, which I think is quite a cool name. And as I understand, Tim got in contact with James, who's at UCB, and said, did he want to set up a team? And there were emails going back and forth. James thinking that the Oxford team would have a big group of people, but it soon turned out it was just Tim. So it's quite a nice name there. But I'll just take you through the synthesis very briefly. So we start off with a cyclopropanation to open up this cyclopropane. They then proposed Suzuki minor cross coupling to take you back to these two fragments here. For this fragment here, they then open that up with a ring closing metathesis to take you back to this intermediate here. They then do a Sekar alylation to break it back to this intermediate, followed by a diboration Suzuki cascade to take you back to these three commercially available intermediates. For this fragment here, they break this bond here using a distereoselective hydroboration, and then these three bonds here with a zirconium mediated cyclization to take you back to this diene here. This bond is then broken using a sort of hydroboration Suzuki cascade reaction to take you back to these two fragments, which are assembled using SN2 chemistry back to these three commercially available compounds. And Dannhauser-Stork transposition chemistry takes this intermediate back to these two starting materials. So it's a real shame that Tim and James can't present today, but well done for getting third place, and yeah, it's great to see some of your chemistry. So our second presenters today are Team GSK, Carbene there, done that. I think, quite frankly, you guys deserve a medal just for coming up with that name. So the team's made up of various people from either permanent members of staff at GSK or members of the GSK Strathclyde reverse case PhD program. So we've got Diane, Darren, Joe, Alfie, Tom, Luke, Will, and Joe. And today we've got Joe, Alfie, Tom, and Luke who are going to be presenting. And their fun quote for the session is, one of our team members won a trip to Los Angeles in a James Bond lookalike competition. So guess which one of us it is. So I'll leave that to you guys to put into the chat box, and we'll see if we've got any any winners for that. So without further ado, I'm absolutely delighted to hand over to Team GSK.
Good afternoon, everyone. Thank you very much for the introduction and to the organisers for the opportunity to share what was a very enjoyable experience with you again. So we're Team Carbene There Done That, and as Oliver said, we're representing a collaboration between GSK and the University of Strathclyde collaborative PhD programme. So I'll briefly outline what we felt were the key synthetic challenges when approaching the retrosynthesis of nidoterpenoidae. So the first of these is the angular triquinane. So this is a motif that's present in several natural products, so with a variety of reported methods for its synthesis. And so we identified that selection of a rapid and stereoselective method for its construction would be essential for a short and efficient synthesis. The 5-3-5 ring system, on the other hand, is comparatively rare, and so it's got limited synthetic strategies associated with it. So here we reasoned that the novel application of known chemistry would be required. And to add to the challenge, this hexacyclic carbon skeleton must be constructed while setting 13 stereocenters. So it was a task that was certainly non-trivial. So our retrosynthesis of nidoterpenoidae begins with reconnection of these two alcohols to form a bicyclic lactone that we plan to use to provide stereo control during the construction of the 5-3-5 ring system via an intramolecular cyclopropanation. This then gives us a molecule that we could disconnect to give two fragments of roughly equal size and complexity. We were then able to identify two key enantioenriched intermediates that we could use to provide diastereoselectivity throughout the synthesis, and that themselves could be synthesized from cheap and readily available starting materials. So those were norbornadiene and this cyclopentenone derivative. I'll now hand over to Luke to present the synthesis of intermediate A.
Okay, so our approach to intermediate A begins with norbornadiene, and we plan on taking this through a palladium catalyzed hydrosilylation and oxidation to give us diol-2. And this is directly precedented in the literature, with the use of the chiral phosphine being the first of two key asymmetric steps in the synthesis. The E quoted is actually taken from the publication as well. You also may have noticed that this initial step uses benzene as the solvent. And so to sort of alleviate the issues around this, we looked into similar reactions and found that a neat reaction is probably the best approach to avoid this. From diol-2, we can do a Swern oxidation to take us through to diketone 3. And from there, we can undergo a carefully controlled Biovilliger reaction to give us access to lactone 4. The difference in reactivity between the ester and the ketone can now be exploited. This is highlighted by an alpha methylation of the ketone to give us compound 5. And from here, we can form a vinyl triflate, which enables an sp2-sp3 cross-coupling with the benzyl protected trifluoroborate salt shown, which is easily accessible from commercial materials. A subsequent alpha hydroxylation using Davis's oxaziridine gets us through to compound 7. A TVS protection of the hydroxyl group under common condition leads us through to compound 8, from which we can form the lithium enolate shown below. As can be seen from the rotating energy minimized structure, the approach of the electrophile is preferable over the unsubstituted 1-carbon bridge versus the highly substituted 2-carbon bridge, giving us the desired stereoselectivity. This is supported by a number of literature examples, and some of these are shown on the left with varying size of electrophile and group in the alpha position. This is the first instance of using the molecular topology to our advantage in order to obtain the desired diastereomer, and this is a theme which we carry throughout our route. Following the diastereoselective methylation, hydrogenolysis of the benzyl group occurs in the presence of the tetrasubstituted alkene, and again this is precedented in the literature. Finally, bromination of the alcohol leads us through to intermediate A, and I'll now hand over to Tom to take us through intermediate B.
Thank you, Luke. For the synthesis of the 5-5-5 fused fragment, intermediate B, as we show top right, where we begin with a precedented Sonneger-Shearer coupling of vinyl bromide to propyne to form E912. We then would take 12 through a selective copper catalyzed hydroborylation to give the terminal boronic ester 13. 13 we would then activate as its BF3K salt 14. The commercially available cyclopentenone 15 would be brominated with NBS with exact literature precedent for forming the brominated compound 16. We'd then couple 16 to 14 in an sp2, sp3 Suzuki to give enone 17. The use of a CBS catalyst, which is derived from the naturally occurring S-proline and borane, could then be used to selectively reduce the enone to give the chiral allylic alcohol 18. This is the second and final enantioselective step in our route, with all further stereocenters set diastereoselectively. With intermediate 18 in hand, we would then propose a diastereoselective epoxidation with a vanadium 4 catalyst and tert-butyl hydrogen peroxide to form the cis-epoxy alcohol 19. This chemistry is developed by Sharpless, and it would traditionally run in benzene, although we envisage the use of toluene as a milder and safer alternative and has similar precedent for performing these transformations. We then envisaged that 19 could undergo a stereospecific semi-pinnacle rearrangement with a catalytic quantity of boron trifluoride, which would provide the chiral beta hydroxyketone 20. This is a key step in our synthesis as it sets two challenging stereocenters, which are then preserved throughout the rest of the route. The precedent for this transformation comes from the synthesis of a prostaglandin derivative, as shown in the orange box. The mechanism proceeds with the activation of the epoxide with BF3, and then the hydride from the bottom face of the molecule migrates to open the epoxide and inverting that stereocenter at the 2 position. The alcohol in 20 can then be facilely protected as a TBS ether to form 21. We then take 21 through a Horner-Wandsworth Emmons to form the alpha beta unsaturated ester 22, and then a careful reduction with diabal would provide enal 23. I'll now hand over to Alfie, who will complete the synthesis of fragment B.
Synthesis of intermediate 23 brings us to a pivotal stage of the route, where a nickel-catalyzed reductive cyclization cascade furnishes the angular 5-5-5 ring system by forming 2 carbon-carbon bonds and setting the key all-carbon quaternary stereocenter of the triquinane. This was one of our first breakthroughs during our research, and we thought that the rapid buildup of molecular complexity in a single step was an excellent disconnection to build our synthesis around. In the proposed mechanism, nickel coordinates to the alkyne and undergoes a reductive cyclization to give this metallocycle. Protonation reforms the aldehyde that can then undergo a second reductive cyclization to the product, with the alcohol formed on the convex face of the nascent bicycle. There is excellent precedent for the formation of a single diastereomer from the racemic starting material, and so the use of the single enantiomer 23 should give the desired product 24 with complete diastereoselectivity. Allylic alcohol 24 can then be oxidized with manganese dioxide to give enone 25 that allows for the conjugate addition of a methyl cuprate with good precedent for the formation of the desired cis-5-5 ring system only. Protonation of the resulting enolate on the least hindered convex face of the bicycle using a sterically demanding proton source, butylated hydroxytoluene, furnishes fragment B in excellent yield. There is precedent for the use of BHT in a kinetic asymmetric protonation, and we have identified contingency plans using a chiral proton source that would complement the unsymmetrical nature of our substrate should the selectivity prove insufficient. With both intermediates A and B in hand, formation of the kinetic enolate of B with LDA and subsequent alkylation on the least hindered convex face of the bicycle gives the alkylated product 26. This reference gives precedent for the alkylation of a sterically hindered ketone, and the one below for the reaction of a kinetic enolate at a ketone with an alpha stereocenter without epimerization. I will now hand over to Joe to complete our synthesis.
Following this diastereoselective alkylation, intermediate 26 is homologated using a Wittig reaction, which is then protonated under mild conditions to give the thermodynamically most stable aldehyde. Taking a look at the below energy minimized structures and Newman projections, it can be seen that for the desired diastereomer, the substituents are able to adopt a more stable staggered conformation. In contrast, the undesired diastereomer is forced to place these substituents around the ring in a higher energy eclipsing conformation. Furthermore, moving back to the desired diastereomer, we can see that it places the aldehyde on the less hindered convex face of the fused bicycle, which we expect to reinforce the preference for this product. Treatment of aldehyde 27 with total hydrazine affords 28, the precursor for the key cyclopropanation step. We now move to the second of the key steps in the synthesis of nitroterpenoid A. Using conditions selected from the literature, the intermediate rhodium carbanoid is generated from hydrazone 28, which undergoes a cyclopropanation to complete the carbon framework of the natural product. Once again, we make efficient use of the bridgehead bicycle to ensure that cyclopropanation occurs on the top face of the alkene. Taking a look at this rotating energy minimized structure, it can clearly be seen that the 3-atom bridge effectively shields the bottom face of the alkene to make certain that it is the top face which reacts. This, in conjugation with the requirement of the 5-3-5 tricyclic core for cis fusion, ensures that all stereocenters will be set correctly. The use of total hydrazones to generate metal carbanoids is well precedented, as is the generation and use of highly hindered rhodium carbanoids. These precedents are depicted on the right for your convenience. We expect that the intramolecular nature of this cyclization will result in a rapid rate of the desired reaction despite the tetrasubstituted nature of the alkene. After serving its purpose as a creative and highly efficient blocking group, we finally open the lactone and reveal the diol by treatment of 29 with lithium borohydride, then perform a global deprotection with TBAF to give nitroterpenoid A. Our synthesis of nitroterpenoid A begins with the enantioselective synthesis of these two intermediates with unparalleled literature precedent for each. It is noteworthy that these two steps are the only occasions where the asymmetry requires installation. All subsequent steps were designed such that they would be highly diastereoselective. Our synthesis then features a nickel-catalyzed reductive cyclization cascade to furnish the angular 5-5-5 ring structure, the cornerstone of our synthesis. The efficient use of the lactone mass diol provides stereo control for a number of steps in the synthesis, but most notably for the key rhodium catalyzed cyclopropanation step to complete the carbon framework of nitroterpenoid A. Our convergent synthesis of this natural product combines two advanced intermediates to ensure a short linear sequence of steps to give the desired natural product an excellent yield from an extremely cheap, commercially available starting material. Thank you very much for listening. We're now happy to take any questions that you have.
That was really nice, guys. Really, really cool nickel cascade reaction there. I've got a very brief question to start off with before I hand over to the other guys. On, I think, slide 5. I think it later turned out to not be relevant, but just wondering about the stereochemistry of, so the methylation of 4 to 5. Is that not going to go the opposite way around? Because you're going to flatten it, you make the enolate, and then surely that would attack from the opposite face from the methylene group that's pointing up towards you. I guess it doesn't really matter anyway because it flattens out afterwards anyway, but or have I just misunderstood that completely?
Yeah, so like you said, it ends up not mattering in this case. But I think there was literature precedent with these bicyclic systems that sort of alkylations in these positions go in the exo position.
Okay.
And that's just sort of, so this kind of highlighted here as well. It's kind of a common thing with these systems.
Fair enough. Cool. So I'll just pass over to Jason and Nessa. We've got quite a lot of comments on the on the James Blunt stuff, but I won't. We won't go through those unless you really want to.
Thanks for that, guys. I have to say I forgot how good these presentations are. So thanks again for putting this out there for us. I had a quick question before we jump into the questions in the comment section on that nickel catalyzed step. If we could just look at that real quick. I think it's slide 9. And it's just, and apologies if I missed this. Can you just run me through the rationale of that initial cyclization and why it goes with giving you that cis enantiomer rather than the other cis enantiomer? So I appreciate that you're in that envelope and you have your TBS. I don't need A values or anything, but what's the rationale for why it's going to go to give you what you have as the second compound in from the left in the middle there? So the nickel metallocycle. So why that one rather than the other one?
I think it's due to initial coordination to the alkyne that's tethered on the top face of the cyclopentane.
Mm-hmm.
And then that adds into your sort of alpha beta unsaturated aldehyde, I think.
No, that makes perfect sense. Thanks. Apologies that I missed that, but it's a great transformation. Excellent. How we doing on the line, Nessa? Anybody coming through with questions for us? Well, you're stuck with one more from me then, and apologies for this. Just on slide 5 that you got there. It's a simple question, and my apologies. For that Baeyer-Villiger going from 3 to 4, why are you predicting that it's going to go with that regiochemistry rather than opening up the ring on the other side? So why does that bond migrate rather than the other one? Thank you.
Yeah, so this is based again off sort of literature precedent with these systems. And it's one of those things again that seems to be common. I don't know if any of you other guys want to add anything to that.
I think it's that the rationale behind that is that the carbon that migrates is tertiary, or sorry, secondary rather, and so has a preference for the migration. Hopefully, does that answer your question?
Answer my question completely. It's the old academic in me that likes to ask these sort of generic questions. So it's everything you learned in first year of organic chemistry essentially. Okay, I want to thank you guys again. That's about it for your time. I don't see any more questions coming through. Just to let everybody on the line know, we are going to have an open Q&A. So if your question was just too complex for you to type in, the teams are going to stick around. You'll be able to raise your hand and ask them more directed questions at the end. But again, I'd like the 130 people that are still on the line. You can hear us all clapping for you. Thanks again for presenting today, guys. Much appreciated. And I'll hand back over to Oliver now. Thanks again.
Thank you.
Thank you.
Thank you.
Okay, so we move on to our final team from the University of Leeds, which is made up of members from both Steve Marsden's group and also Adam Nelson. Some familiar faces there from when I was back in Leeds. And their team name is Accident and Convergency. So we've got Andrew Gom, Chloe, Scott, Alex, and Andrew. And their fun quote, I guess, is none of us have worked on total synthesis projects before, but one of us has been on Eggheads. So again, if you want to put those questions in the questions tab, go for it. I think, yeah, without further ado, I'll hand over to you guys.
So hello everybody, and first of all I'd just like to say a big thank you on behalf of Team Accident and Convergency for joining us today. So Oliver gave us a nice introduction to niditerpenoid A at the start of this session, but we would just like to talk you through a little bit about our thinking and our approach to the molecule. So niditerpenoid A is comprised of a hexacyclic carbon framework which is fully saturated and has very limited heterofunctionality. It's also comprised of both an angular and linear triquinane ring system, and there are very limited literature examples of compounds which contain both of these ring systems. There are also 13 contiguous stereocenters, 4 of which are all carbon, and this generates 11 neopentyl positions. All of these considerations resulted in 3 strategic approaches that we took to this molecule, which you can now see in the top right-hand corner of your screen. Firstly, we wanted to install challenging quaternary stereocenters as early as possible, which are labeled as 8 and 15 on your molecule, as we hoped this could inform some of the stereochemistry further down the line. Secondly, we wanted to set the challenging methylated stereocenters, which you can see as 11 and 16. Again, we wanted to do this as early as possible to inform future stereochemistry. And finally, the 5-3-5 ring system, which is quite unstable to certain reducing conditions, such as hydrogen, and the acids also cause this ring system to pop open. So we wanted to install that as late as possible. So I'm just going to talk you through some of our key retrosynthetic disconnections. So as I said, the 5-3-5 ring system is unstable, so that was one of our first disconnections, and we envisaged that a metal catalyzed cyclopropanation reaction could facilitate this in a forward sense. We would install the chain required for this reaction using a cross-coupling reaction. We then decided to break the C ring system in 2 different positions, as this would allow us to install the D ring system as a complete ring. And we thought a decarboxylative Giese coupling would allow this, as the radicals can react at the quaternary center. The penultimate retrosynthetic step that I'd just like to draw your attention to is this radical addition and retrohydrocyanation, as this would allow us to set that challenging methylated quaternary center. Finally, we thought a gold catalyzed 5-endo dig cyclization would let us set our AB ring system with the correct stereochemistry. Luckily for us, compound 9 can be made from this beta keto ester, which you can see in the top right-hand corner of your screen. So this has a full literature synthesis, which Alex is going to talk you through, along with the forward synthesis for rings A and B.
Thank you very much, Chloe. So before I talk through the synthesis of rings A and B, I just want to draw your attention to the bottom left-hand side of the screen, in which the references that we've used for our precedents will pop up alongside the corresponding reactions. So as Chloe mentioned, to start with, our first series of reactions have been taken directly from the literature. So that's everything you can see on screen now. So that would involve the incorporation of our chiral auxiliary, which you can see at the bottom, followed by an Arbuzov reaction to deliver the phosphonate. From here, we will carry out a Horner-Wadsworth-Emmons reaction with our other coupling partner, which we could make in 3 steps, followed by a 1,4 addition and a Dieckmann cyclization to furnish the product on the right-hand side. It's worth mentioning here that both of our starting materials are very cheap, and we can recover this chiral auxiliary at a later point. We then plan to carry out protection of the ketone using ethylene glycol, followed by an ozonolysis reaction to furnish the aldehyde. From here, we would introduce lithium acetylide, followed by oxidation to the ketone using DMP. We then envisage the addition of our methyl substituent via the addition of methyl lithium. So this is very similar to a reaction carried out in the literature, which you can see on screen now, in which they obtained a high DR. So they rationalized this result using Felkingham control, and we've used that model too for ours. So you can see from our model that we've depicted our bulkiest group to sit perpendicular to the carbonyl, and then illustrated that methyl lithium will attack on the less hindered face. This will deliver our desired stereo outcome, as you can see on the right-hand side there. Simply after this, we would just protect the alcohol using TBS, followed by a transesterification reaction in which we could recover our chiral auxiliary. We would then use trityl tetrafluoroborate to cleave the ketal and to deliver the ketone. So once we'd synthesized ring B, we then plan to append ring A to it using this gold catalyzed 5-endo dig approach. So this is work that's been carried out in the TOS group. So you can see there's a couple of examples on screen there in which they achieve a single stereoisomer from their reaction. So to try and illustrate this, we've drawn a cycle. So you can see that our compound can either sit in the keto or enol form. It can then undergo coordination via the alkyne to gold, followed by a 5-endo dig cyclization, which will deliver the more stable cis-fused product. From here, deprotonation will afford our product as a single stereoisomer. Then following that, all that would be left to carry out would be a simple hydrogenation, which would afford our saturated AB ring system. And with that being said, I'll now pass over to Scott, who will talk you through the synthesis of rings C and D.
Thank you, Alex. So to begin the synthesis of ring C, we first had quite a challenging stereocenter to prepare at the position where the ketone is in ring B. So after some consideration, what we decided to do was to perform a Wittig reaction to transform that ketone to the alkene, and then use Baron's reductive olefin coupling chemistry to allow us to generate that tricky stereocenter. So if we could couple together between that alkene and acrylonitrile, then using a steric argument, the largest substituent should be placed on the least hindered face of the molecule. So in our ring system, that means that the ethyl nitrile group that's made via this chemistry should be placed pointing down on the convex face of the AB ring system, which is sitting as a bowl-like structure, therefore putting the smaller methyl group pointing up on the topmost hindered face of the molecule, therefore setting the stereocenter as required. So with that stereocenter now set, we then wanted to use Bill Morandi's retrohydrocyanation chemistry. So this uses a nickel catalytic cycle to effectively remove hydrogen cyanide from our molecule and generate an alkene reaction handle for us to continue our synthesis. We would then perform ozonolysis to generate the aldehyde, followed by a Seeforth-Gilbert reaction with the O'Hara-Bestman reagent to generate the terminal alkyne. Subsequent ester hydrolysis, followed by coupling of the corresponding acid with N-hydroxyphthalimide, then generates a redox active ester that plays an important part in this key step shown here. So now we have our redox active ester in hand. What we wanted to do next was to perform a photoredox decarboxylated Giesa coupling, and that was to allow us to achieve two things. Firstly, to help us generate that tricky all-carbon quaternary center, and we wanted to use radical chemistry to do this, as radicals are known to be really good at reacting at highly hindered and congested positions in molecules. And secondly, we wanted to use this Giesa coupling reaction so we could add in this 5-membered ring cyclopentanone substrate to our A and B ring system all in one step. So under these reaction conditions, our redox active ester will fragment to generate the tertiary radical, which can then selectively add into the top face of our cyclopentanone substrate, which is directed by that OTBS group, which is pointing down, therefore facing away from the AB ring system to avoid any unwanted steric clashing between these two groups, therefore leading to the diastereoselective nature of this reaction and giving us the diastereomer that we want. So with that, we would then iodinate our alkyne to give the vinyl iodide and eliminate out that OTBS group to generate an enone. This then sets us up to do a lithium halogen exchange followed by a 1,4 conjugate addition into this enone, where we could trap our enolate out with TMS chloride, and this reaction stitches together our C and D ring system, leaving us with that sialyl ether on the far right side of our molecule. We could then perform a regio and stereoselective iridium catalyzed hydrogenation of the alkene, which should selectively keep that sialyl ether in place, therefore allowing us to use Corey's chemistry to transform this group to the corresponding vinyl triplet, where under these reaction conditions, the OTBS group should also be cleaved to subsequent reprotection of that alcohol to give the O-acetal or complete the synthesis of the middle ring C and D. So with that, I'll now hand you over to Andrew, who will talk you through the final stages of our forward synthetic route.
Thanks very much, Scott. So if you remember back to our retrosynthetic analysis, we were going to use this vinyl triflate species here to undergo a palladium catalyzed cross-coupling reaction in order to install our diazo moiety, which would then undergo intramolecular cyclopropanation. So we envisaged using Gary Molander's chemistry from his 2005 JOC paper to install this 1,3-diene. So this paper demonstrates that you can have stereo retention of the geometry of your double bond after you perform the cross-coupling reaction. And we were quite confident that you could use the vinyl triflate and your potassium trifluoroborate species as suitable coupling partners. So then we deprotect our ester using TFA, and then we produce the acid chloride using oxalyl chloride, and then trap it out in situ using diazoethane to form our diazo species. So now we come to quite an important step of the reaction. So we've got our intramolecular cyclopropanation, and we decided to use conditions from Thomas Hudlicki using catalytic copper ACAC. So we were confident, based on literature precedent, that we would get the correct relative stereochemistry from this reaction, but we thought we'd actually get the correct absolute stereochemistry modeling off these two different reaction pathways down here. So on the right hand pathway, you can see that we have attack from the diazo species from above the plane of the double bond. And now we have clashing of this methyl group here with the bold configuration of these two 5-membered rings. Plus we have a great ring strain placed around our alkene in order to get into this reaction conformation in the first place. Alternatively, you could have the left-hand side pathway where you have attack from below the plane of the double bond, and this actually is the desired outcome, and we believe also the most likely reaction outcome too. So finally, next we go to our 1,4 addition of our cuprate species here. So using this Grignard reagent, we believe that we'd get addition to the bottom side of our molecule. So if you look at this reaction pathway here, we have the bulky cuprate species delivering to either the top or bottom face of our cyclopentanone. The 5,3,5 ring system causes quite significant steric clashing on the top face, so we're quite confident we would get delivery below. And actually, we can see from McCagan Journal of Chemistry that we have a good precedent for this too. penultimate step now is reduction of our ketone with lithium. So we believe we'd get the correct S alcohol forming as per this reference here in the Polish Journal of Chemistry, and we rationalize this outcome due to the small nature of our hydride nucleophile, therefore preferring pseudo-axial attack. And our final step of the synthesis is dihydroxylation of our alkene. So for this, we really relied on some work from Rob Patton to rationalize the correct stereochemical outcome. So he was able to show by low energy state conformations on a similar substrate that when you have your cyclopentanone with this alkene isoprene species substituted off it, that the isoprene alkene is coordinated down as opposed to the five-membered ring. So now you have a choice of attack with the osmium tetroxide from either in the plane of the double bond or from behind it. And you can see the two different reaction outcomes here in this diagram. We believe that actually the steric clashing of the rigid carbon backbone basically means that we would get attack from in the plane of the double bond, which would give us our correct stereochemical outcome. So thank you for listening to our synthesis. I think we've been able to show, hopefully, that we can make this molecule from cheap starting materials. We've been able to find what we think is decent precedent for all the key steps of our synthesis, which we made quite a priority. We've been able to showcase what we think is some really exciting chemistry, in particular to make these two all key carbon quaternary centers. We use some exciting radical chemistry, which is nice to see. We're acutely aware that we have basically a long linear sequence of steps. However, when we applied Phil Barron's ideality metrics to our synthesis, due to the high number of skeletal CC bonds that we're forming, actually our ideality we don't think is too shabby, especially when you compare it to other first-in-class sesquiterpenoid total syntheses. So yeah, we're really happy to answer any questions, and thank you very much to the SCI for sorting out all the technical gymnastics that this required. So thank you.
Hi guys, that was absolutely fantastic. Really, really cool chemistry in there. So I've just got a brief question. So the, do you mind just going back to, I think it was the final stage. So is it also possible the alcohol could direct into the osmium and direct it onto that side, so you have electronic arguments as well as the steric clash from the other side? I guess it's not that close, but
I don't know, to be honest. Yeah, I have no idea. I can show you the precedent that we relied on. So we relied on this precedent here from Rob Patton, and yeah, I'm not sure if the alcohol would do that, to be honest.
Cool, really, really nice route anyway. Okay, so I'll just pass over to Jason and Nessa.
Great, thanks again for another great talk and showing everyone you know, a little bit of what the competition looked like on the day. Just had a quick question, if I could, on slide 25, if you don't mind, and then we'll go to any questions that come through on here. Just sort of curious. So you're going in the first two steps there. You know, you're doing that cross coupling, and then you're treating with TFA. So you have both acid and basic conditions in those first two steps. Are you worried at all about a 6-pi electrocyclization to form a pyran in that system?
Yeah, no, that's certainly something we thought about. We couldn't find any direct precedent for that to be a particular outcome, but yeah, in theory, it is looking set up for that. But no, we didn't find anything, particularly off 5-membered rings. Couldn't find any precedent.
Yep, excellent. Yeah, the close I cheated, if I'm honest. The closest I could find, it was benzylic. So I think that's a reasonable answer. All right, Nessa, how are we doing on any questions? Or are you there, Nessa, I should ask?
I am there. Sorry, I think my audio disappeared earlier. Oh, I've got one question. I think I might ask this one that's just come in from Spencer Napier. Do you know what precedent there is for the radical decarboxylation? This is the intermolecular reaction with the 1,4 system compared to intramolecular reaction with the adjacent alkyne to form the cyclopropyl ring. We definitely need to have a look at this, don't we?
Yeah, so we couldn't really find anything that was on our mind as well, but we couldn't really find anything that would suggest that would go in a priority over the intramolecular version. So I guess you could say a similar thing could happen in the precedent here with the alkene as well, but that doesn't happen. So I guess it's just one of those things, really. You'd have to try it, wouldn't you, to see if it actually did that kind of thing or not.
Yeah, I can believe that.
Yeah.
Looks good to me. Jason, we may have time for just one more, perhaps.
Yep, we got another quick minute or so. Let's give anybody a last chance here. I think what I'll do, guys, if you don't mind, I'm going to let you off the hook. You have 30 seconds to spare. It's not too bad. I'll throw back to Oliver, and that way we can open it up in case there's any questions for you guys or any of the other teams, and that gives us a few extra minutes so that we stay on time with the webinar in total. So thanks again. We have 127 claps for you, so that was great.
Thank you.
Thanks for the presentation, and hopefully we'll have a few more questions for you in just a minute. Thanks again. Thanks.
Cool. Right. So I think we'll wrap up, and then at the end we'll take if we have any extra questions, we'll take those via the audio. So just a big well done and thanks for everyone who presented today, and well done to the other teams. So we've got Eva takes on a roll. They had 2 teams at the final. We also had teams from Manchester, Charles River, Bristol, Nottingham, and St Andrews. So well done to all of you guys for getting to the final. A reminder, we've got so for the 2021 retrosynthesis competition, we have the molecule being released on the 28th of September. So keep your eye out for that. And then on the 19th of March, that's when the competition will be. We don't know yet where that's due to be held. I think it's supposed to be the SCI because
plan is SCI headquarters, I believe.
Yeah, I didn't know whether that was changing because they had to move it to the SCI this year. But I guess it depends on the whole lockdown situation anyway. But that'll be released shortly. And then just so everyone's aware, we've got our final talk in the webinar series next week, which I suppose is a bit of an end of an era over these last 12 weeks. This is going to be a really, really good one from Neil and Anya from Merck on electrochemistry and biocatalysis with this mad sort of telescoped crazy chemistry. So really not one that you want to miss. And yeah, I just wanted to take the opportunity to thank all of our speakers, and also Theo and Jason Camp, Nessa for helping out with the organisation of today's session. It's been a great talk with some really, really cool chemistry, different approaches of making niditerpenoid A. And yeah, if anyone's got any questions and would like to raise their hands for any of the 3 teams, please go for it. And yeah, we'll hopefully get through some of these. Same for any team members that we have. If you have questions for your other teams, please go for it. If not, I think we might wrap up.
Yep, I think everybody did a great job today, and just want to thank all the teams again for showing up, and a quick again shout out for this year's competition. So hopefully, if you're on the line and this looks interesting, please feel free to apply for this year's competition.
Cool. Thanks a lot, everyone, and hopefully see you next week.